In this video, we are studying chapter 4.7, Coordinates and Change of Basis. Our learning objectives for this chapter section are to represent coordinates in general and dimensional spaces, find a coordinate matrix relative to a basis in Rn, the set of n-dimensional real numbers, and find the transition matrix from the basis B to the basis that we call B prime in the n-dimensional real numbers Rn. So we're going to let B equal a ordered basis of V1 through Vn of vectors for a vector space V. And we're going to let X be a vector in V such that X is comprised of scalar multiples of each vector V. So C1 V1 added through Cn Vn. So these scalars C1 through Cn are called the coordinates of the vector X relative to or with respect to the basis B. And the coordinate vector or matrix of X relative to B is the column matrix in Rn, whose components are the coordinates of X. So we're going to have column vector X with the B in the subscript, be the scalar C1 through Cn. So we call this a coordinate vector, or we can think about it as a column matrix of X relative to B. So let's take a look at an example. So the coordinate matrix of X, X1 through X3, relative to the standard basis, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1 in R3, is simply X column matrix subset S here, a little S here in the subscript, is X1, X2, and X3, because we can write X1 as X1 times E1, where we're using the standard basis, plus X2 times E2, where we're using the standard basis, so E2 is 0, 1, 0, plus X3 times E3, because E3 is 0, 0, 1. So with the standard basis, it's really simple to write the coordinate matrix. When we use more complicated bases, this is where we are going to need to figure out these scalars that multiply through. In the next example, we're going to find the coordinate matrix of the polynomial 2x squared minus 5x plus 6 relative to the standard ordered basis. For the second degree and less polynomials, that standard ordered basis is 1, x, and x squared. So our constant is 6, so we're going to have 6 times 1. So our scalar here is the 6. We've got minus 5x, so we're going to have minus 5 here in the second position of our coordinate matrix P. And then we're going to have, this should be a 2 here, I believe, for the x squared. So we got a little typo there for the third scalar. So just notice when you're working with the standard order basis, for the polynomials, it starts with 1 and then goes x and then x squared. It would go up to x third if you're in P3 and so on. So make sure you check the order, because typically we write polynomials in descending with the highest order. But when you're working with the standard basis, it's going to be ascending from 1 to x squared in the next term, and so on. Okay, let's, in the next example, find the coordinate matrix of A, where A here is going to be this 2 by 2 matrix, 8, 2 in the first row and 1, 7 in the second row. And then we're going to do that relative to that standard ordered basis for the 2 by 2 matrices, the 4 matrices with 1s in each position. So we've got 4 matrices on our basis for M 2 by 2 matrices. And then we just multiply each scalar here times the corresponding position for the standard basis. So since we have 8 in position 1, 1, we get an 8 here multiplied by the first standard ordered basis matrix. Since 2 is in row 1 position column 2, we got a 2 here in front of the matrix 0, 1, 0, 0. Similarly, since 1 is in row 2 position 1, we use the scalar 1 here multiplied by the standard ordered basis matrix 0, 0, 1, 0. And then since 7 is in position 2, 2, we have a 7 here multiplied through by 0, 0, 0, 1 standard ordered basis matrix. And so we would write our column vector, or our column matrix, we want to call it that, A, as the coefficients listed in the column. So again, what's important here, as what was important in the second example, is to make sure your scalars or coefficients here match the order of the basis. So since 8 goes with 1 in position 1, 1, that gets multiplied through, we got to make sure we have 8 in the first position of this column matrix. Okay, now we're going to look at another example. So given that the coordinate matrix of X in R2 relative to the non-standard basis V1, V2 equals 1, 0, and 1, 2 is column vector 3, 2, find the coordinate matrix of X relative to the standard basis that we're going to call B prime. So that's going to be U1 and U2, and we're just using U here to differentiate it from the V's that are in B. And so those vectors are 1, 0, and 0, 1, and we're going to call that also S. You can call it B prime or S, your choice. Okay, so X sub B is 3, 2 as a column vector means that 3 and 2 are our scalars that get multiplied by V1 and V2. And then we've got V1 and V2 right here. So here's V1, the vector 1, 0, and here's V2, the vector 1, 2. And so we can multiply through and see, okay, it's going to give us 5 and 4 as our vector values. So our next step now is to take the resulting vector 5, 4 and break that down into vectors U1 and U2 that are 1, 0, and 0, 1. So that's pretty easy because these are the essentially basis vectors that are the standard ones. So it'll be 5 times 1, 0 and plus 4 times 0, 1. So we can write this as 5U1 plus 4U2. So our X B prime is a subscript as a column matrix or a column vector is going to be 5, 4. So now if we want to visualize this, how we're shifting this around, we can think about 5, 4 as 5 times the x-axis, or 5 times 1, 0, plus 4 times 1 on the y-axis, or 4 times 1, 0. And so here's our visualization here. So let's see, we start with the first vector here that's at 3, 2. Let's see, can you see my writing there? I'll switch over to black ink. So this point here, this is a vector because it's starting at the origin. And notice we're in this angled blue grid here. So that's representing our original B here that was this non-standard basis 1, 0, 1, 2. And then we're shifting to what we think of as a standard basis. So that's what the second picture is supposed to be showing you, is like if we transition back to the standard basis, then we end up here at 5, 4 for the endpoint of our vector. I uploaded a video from 3 Blue 1 Brown that I think shows this a little bit nicer visually than my attempt at creating pictures here, but you can sort of get a sense at how we stretch and manipulate when we are changing bases. So another method that you could do this is you take the coordinate matrices relative to B prime of X equals 3V1 plus 2V2. And we tend to do it this way because it's a little bit easier to put them all together in a matrix. So V1 here is really, V1 transpose, and this is V2 transpose because we're treating them as column vectors. It's not necessary to write out the transposes there, but know that you're putting these vectors in the columns now. And then we do that to obtain, okay, well, what are the values relative to B prime? And so we can put in our V values here, 1, 0, and 1, 2. This is our non-standard basis. And then multiply that by our values 3, 2, and we get out our 5, 4. You can check the multiplication there. So you can see how we're going to be able to use matrix multiplication to find these change of bases. So let's break down kind of our steps there that we just did in the last example. So our X column matrix sub S, try to make my S a little more clear here, is this matrix or vector. You can think about it as the constant C1 V1 plus C2 V2, where The V's are the vectors from our original basis. So it's the S here. And then we want to try to transition them to the next basis, the basis that we're changing to. So we think about them as column vector V1 sort of relative to S, combined in a matrix with column vector V2 relative to S. And then this gets multiplied by our constants, C1 and C2. And then we're able to think about that as matrix times the X column vector in our new basis. So we think about that as, we call it the transition matrix, and we'll talk about it more, is going from B to our new basis S. So we do the inverse of this transition matrix and multiply it by our X column vector in the new basis. So that's the process we went through. Here's a more nice typed version of what I just went over. So this whole procedure is called the change of basis. We say it's from B to B prime. So back here I was using S as my original, but it could just as easily be B prime. So given this X in the basis, we found X to B prime using an equation of this form, that X B prime is P inverse, this inverse of what we find is a transition matrix, times the X original vector in the original basis. And then this P inverse is the vectors relative to the new basis B prime. So this P inverse is called the transition matrix. So we're going to look at more examples. So let's look here at this next example. So given that the coordinate matrix of X in R3 relative to the standard ordered basis, what we can call E1, E2, E3, is X sub B 1 to -1, we want to find the coordinate matrix of X relative to the non-standard basis. That's going to be U1 is 1, 0, 1, U2 is going to be 0, -1, 2, and U3 is going to be 2, 3, -5. So we're moving from our usual 1, 0, 0. This is our E1, 0, 1, 0. This is our E2, our standard bases here. And then 0, 0, 1, this is our E3. So we're moving from these standard ordered bases to this non-standard basis now that's given us as U1, U2, U3. Okay, so our first step is to write X as a linear combination of the vectors in B prime. So we're going to take U1, U2, U3 from down here and put them as column vectors in a matrix together. And then we're going to multiply that by C1, C2, C3, where C1, C2, C3 are these constants we're trying to find. So we put the U's values over here into column vectors or column matrices, if you want to think about it that way. This right here that I just circled in blue is just kind of the notation to show we're going from a transpose vector to a column matrix. When you're problem solving, you don't have to write out these intermediate symbolic steps, although you're welcome to. So then we know that our original X column vector that we're working from in the basis B with the standard ordered basis is 1, 2, -1. So we've got that here. And then we're multiplying it by our U1, U2, U3 put into a matrix. So at this point, our matrix is P. And then we're going to multiply that by the scalars that we're trying to find. So it makes sense working backwards. To find these scalars, we're going to have the inverse multiplied by our original values here. So here's our P inverse matrix, and here's our original values. And of course, you can use SIMPy to do calculations like this. So you can go verify in SIMPy the inverse of this matrix times our column vector here from the original basis, the 1, 2, -1, gives us our new result over here. So this is what we were trying to find, these are our scalars. So these are the scalars that are going to allow us to change the basis. So here they are right here. And so that's our column matrix that's going to change from the standard basis to this new basis, U1, U2, U3 down here that we're calling P prime. Okay, and so in general, we found this relationship that if we take our basis and break it down into the pieces, we can say, oh, this is U1 in U1, U2, U3, and the original basis multiplied by this scalar, the set of scalars that we're using to help us transition. So we have this relationship that our, if we're going the forward direction, our original basis column vectors is a transition matrix times the new scalars that we're trying to find. And so this is our transition matrix where we put in the U's as column vectors. And then we saw, of course, that to go backwards, we do P inverse times the original basis. So to find the new scalars and the new basis, our formula here is just reversing this to get P inverse times X values in the original basis that we started with. So in the next video, we'll take more look at the transition matrices and see how to do calculations.